Hi, so today we're going to learn about the relationship between derivatives and integrals. And I would say that this topic is easily the most important topic in calculus, but it is also one of the most confusing topics to learn. So, the best way I think to start is just to do an example. So, let me make a coordinate system real quick. Okay, so this example will be a position and velocity graph. So this graph will be position with respect to time, and then this graph will be velocity with respect to time. So let's say that this particle, we could just say it's a car or something, has a position over time that looks like this. So x of t is going to be 2t. That's the position with respect to time of this. So 1 t is equal to 1 will be x equal to 2, and then it would just be this all the way up. Okay, so now if we try to find the slope of this graph, that is not too bad. We could just find the rise over run. So the rise here is 2 and the run is 1. And since this is a linear graph, the slope will be the same for the entire graph. So for the v velocity versus time graph, we will plot the slope of the position versus time graph, which is 2 for all t. And that makes sense because dx dt is the same thing as velocity, which in this case is 2, because dx dt is just the slope of the graph. So now, how are these two things related? So we know that we took the derivative of the position versus time graph to get the velocity versus time graph, which is not too bad. But then now, how is the velocity versus time graph related to the position versus time graph? So it's related by the integral. And what I mean by that is, since velocity versus time represents the slope of the position versus time graph, 2 is the slope. And if we move in time by one interval, let's say 1 second, let's say this is in seconds. If we move over 1 second and we multiply by the rate of change of the position versus time, then we know that the total distance that we get by moving over 1 second is whatever we get after multiplying the slope. So let's say that we are at 2 and we move over a time by 1. The area that we get from this graph here is the change in y for the position versus time. So let me just write it in another color. So the area here is the same thing as the change in x here. The area is equal to the change in x. And this makes sense because this graph represents the change of x by a certain time. And that's exactly what's happening here. After we move a certain time, we change by that amount x. Another way to look at it is just without any derivatives or anything. It's just this, right? And then since this is equal to 2, we just multiply this by the amount of time that we passed. And this, in this case, it's 1 second. So it's 2 times 1. So, sorry, this here is not equal to this. The way that it will be equal is if we do something like this. Because the x dt is 2, and then we multiply that by a change in time here. And in this case, it was just 1. So yeah, that is how it's related. So in this example, it's pretty clear to see, but how will this be abstracted to other functions? So other functions that don't have a constant slope, like x of t above does. So I'm going to make a coordinate system real quick. Okay, so we'll do a position and velocity example again, but instead of having a constant slope for x versus t, we're now going to have a quadratic slope. Okay, so here are the points on the quadratic function. And now, actually before that, we'll just write what the function is. So x of t is equal to t squared. You could verify yourself that this is the function. And then if we take the derivative of this function, so dx dt, we get 2t. And this is the same thing as the velocity function. Okay, so now, yeah, let's just draw this function. It's going to look something like this. 1 will be at 2, 2 will be at 4, 3 will be at 6, and then 4 will be at 8. So yeah, this is the slope of x versus t. Yeah, this is the function of the slope. So we could use the same methodology and idea as the previous example. So let's say that we start at t is equal to 1 and we end at t is equal to 2. And we want to find the change in x that has happened here. We know that delta t is 1 since we moved over just a length of 1 in t. And we know that the amount that x changes as the amount of time changes is 2t. So all we have to do is multiply by the slope that we get of x versus t. And the slope that we get for x versus t in this interval is modeled by this here. So the way that multiplication of this is represented is just by taking the integral of this here. So if we think about it as shorter and shorter time, we know that by multiplying this value here, we're multiplying it by the slope of x versus t. And let's say that and by taking the integral, we are multiplying it by shorter and shorter intervals of time. Like a rectangle will be something like this, and the area that we get is going to be something like this. And this area will be the same change in x that we get here, just like the previous example. Yeah, the area will be the same as the change in x here. The area. And the reason why we have to use integrals for this is because the slope changes with respect to time. Imagine if this was instead a curved line, then we would for sure need to do an integral for this, because there is no polygon that models the curved line like that, or at least no normal polygon. So yeah, that's why the area, or that's how the area is related to, the area is related to the function that was originally taken the derivative of, because v is just the function of x versus t that was taken the derivative of. So yeah, that's pretty much the intuition behind how derivatives and integrals are linked. We use the derivative to get to the v function, and then we take the area to find how much has changed whenever, or how much has risen as we move over in the t position, t axis, how much x is changed. And whenever we do take the derivative of a function, its solution will always be unique because there is no other way to represent slope. But imagine if we took the area from the interval from 1 to 3, right? So as we start at 1 and then we go to 3, the area that we get will represent a change in x. But that change in x could happen at any position in x. So for example, if we started at if we drew this exact same graph, but we shifted it up by 2, and we would get something like this, right? And if we take the derivative of this purple graph, it'll give us the exact same graph as the graph that we have right now on the right. The slope will be the same because, as you can see, the slope of this graph is the exact same as the slope of the initial first graph. But whenever we take the area of it, we can arrive at an infinite amount of functions that represent that same slope. As you can see here, we only did one other representation of the function, but you can imagine we could shift this function higher or we could shift it lower, and we will still get the same slope function for all of these functions. But whenever we integrate it, we could get any one of these functions because this just represents the change in x. The change in x will always be the same. So if we start at 1 here, the change in x here as we move over will be the same as if we started at 1 here, and the change in x will still be the same distance. Same thing here. The change in x, change in x will still be the same as the change in x here. They're the same. So that's the reason why there is a unique representation when we take the derivative, but there is not a unique representation when we take the integral. That's usually why some people get points off. They don't add the plus c, and plus c is what represents the non-uniqueness of whenever we take the integral. So taking the integral of this dx dt by dt, what we get is t squared 2, and then we have to put a 2 on the bottom. These 2's canceled, and then we end up with the original function here. But we have to add a plus c because of the non-uniqueness. Okay, so that's pretty much the relationship between derivatives and integrals. I would say this is, in my opinion, the most important aspect of calculus. This will be used not just in calculus, but in physics, in differential equations, because the world is built upon calculus, and the relationship that the world has with each other is the relationship between derivatives and integrals. Oftentimes initially this is pretty confusing, but I hope this helps a little bit. Thank you.